Now we're going to work on the second question from the 4.4 notes. We're going to graph the function f of x equals x times e to the negative x. We're going to follow the same 4 steps that we did above, which is, first of all, figuring out where this function is increasing and decreasing. That relies on the first derivative. The first derivative is going to need the product rule. That's the first piece. That didn't work out very well. This is the first piece, and this is the second piece. And so we are going to use the product rule. So the product rule says take the first factor times the derivative of the second factor. The derivative of e to the negative x is negative e to the negative x, plus the second factor, so e to the negative x, times the derivative of the first factor. The derivative of x is just 1. Okay, so I can write this a little bit better. It will say negative x e to the negative x plus e to the negative x. Let's go one more step. E to the negative x, factor that out. It's the greatest common factor because it's here and it's here. And that's going to leave you with negative x plus 1. Okay, so we're trying to figure out where this function is increasing and decreasing, right? So that means we want to figure out where this function is equal to 0. And then we're going to test on either side of that critical point to tell us if the function's going up or if it's going down. And so this derivative is equal to 0 when x is equal to 1. All right, so now you set up your number line, divided at 1, that's your critical point. That's potential relative max or min. Before 1, you have to figure out if this function's derivative is positive or negative. All right, so let's choose a test point like 0 because 0 is less than 1. So if I plug 0 in for the x variable right there and right there. If you plug in 0 into the x's for your first derivative, do you get a positive answer or a negative answer? And so you end up getting e to the 0 power, which is 1, times negative 0 plus 1, which is still just 0 plus 1, which is positive. So you ended up getting 2 positive results. This is positive and this is positive when I substitute something like 0 in for the x's. And so that's going to give you a positive product, which means your graph is increasing over that interval. Sorry about the dogs. Next, you choose a point that is bigger than 1. So let's get rid of this. Choose a point that's bigger than 1, substitute it in for the x variables into the first derivative, such as maybe a 2. So if I plug in 2 for the x into e to the negative x, I end up getting e to the negative 2 power, which is positive. If I plug 2 in for the negative x plus 1 factor, I end up getting negative 2 plus 1, which is negative. The product of a positive and a negative value is negative. Now your graph is going down when x is bigger than 1. You've identified the interval that it is increasing from negative infinity to 1. It is decreasing from 1 to infinity, and therefore x equals 1 is a relative max. And the corresponding y value would be 1 times e to the negative 1. You're substituting this back into the function at the beginning for x. And 1 times e to the negative 1 power is approximately 0.37. So the ordered pair for the relative max would be 1, 0.37. I want to point out something back here where we talked about where the interval is increasing and decreasing. I could have written that using inequalities. It is increasing when x is less than 1, and it is decreasing when x is bigger than 1. So get used to using either notation. That will help you out when you do the online Connect Math homework problems. Okay, the next step said to figure out where the graph is concave up and concave down and where the inflection point occurred. And that occurs, or that is determined where by using the second derivative. Okay, so the second derivative of the function. We are going to go back to, let's highlight this part of my derivative. And I'm going to take the derivative now of that expression. So the second derivative is going to again use the quotient rule, or not the quotient rule, the product rule, sorry, the product rule, because this is my first piece and this is my second piece. Okay, so the product rule says that you want to take the first piece times the derivative of the second piece, which is just -1, plus the second times the derivative of the first. Okay, now we simplify this a little bit better. Let's write this as -e to the negative x minus e to the negative x times the quantity -x plus 1. I'm not going to distribute that because I am going to factor out the common factor, which is, let's take the negative with it, -e to the negative x from here and from here. And that's going to leave you with +1 plus -x plus 1, and that is equivalent to -e to the negative x, that's the greatest common factor we just brought out, and then these parentheses that's left over can be simplified to be 2 minus x. Okay, so the whole point now was to figure out where the second derivative is equal to 0, because that's going to give you a potential inflection point. And so this is equal to 0 in only one place, when x equals 2, right? Because this first factor does not have any solution. There's nowhere that that factor is going to equal 0. No value of x is going to work. The second factor, 2 minus x, is equal to 0 when x is 2. Okay, so that gives you your potential inflection point. You're going to put that on a number line. You're going to figure out the sign of the second derivative when you are on the left side of 2 and when you're on the right side of 2, right? So you're going to plug in a test point into your second derivative function, which is this. So if I plug in a value that's less than 2, I end up getting a negative result for the first piece and a positive result for that second piece, and overall my answer is going to be negative, which means my graph is concave down. Okay, now let's choose a value that's bigger than 2. Plug it in for the x. E to the negative, whatever test point you use, is going to be a positive result. But then this says make it negative. So overall your answer is going to be negative. Over here, plug in a value that's bigger than 2 for this x. 2 minus something such as 3 is going to give you a negative result. And overall your answer is going to be positive, which means your graph is concave up. And so let's finish this in the same order. So the graph is concave down when x is less than 2. The graph is concave up when x is bigger than 2, and so that means that x equals 2 is an inflection point. And the y-coordinate of this inflection point is found by substituting the value 2 back into your function at the beginning. And so 2 times e to the negative 2 is approximately, use your calculator for this, 0.27. So the ordered pair for the inflection point is 2, 0.27, rounded. On to step number 3. Find the x-intercept and the y-intercept. The x-intercept is found by setting the function equal to 0, solving for x, The only solution we get is when x equals 0. So the x-intercept is 0, 0. The y-intercept is found by substituting 0 into the function for x. 0 times e to the negative 0 equals 0. The y-intercept, 0, 0. We already knew that because 0, 0 from the x-intercept is also going to be considered the y-intercept. Next step is to figure out the horizontal asymptote. Sorry about that. Okay, the horizontal asymptote is the end behavior of this function, right? And so we want to figure out what happens as x goes to here. As x goes to infinity, what happens to the function? So this is figured out by substituting a large number into the function for x, such as 100 or 1,000 if your calculator will allow you to do that. And you're going to find that the output value, if I substitute in 100, is approximately 0. My function, f of x, approaches 0. And that's just by using my calculator. I substituted 100 into the function for x because 100 is a large number. So since your function approaches 0, that gives you the horizontal asymptote, y equals 0. We don't have to check the left side of this graph because I will not have different horizontal asymptotes. Once I found one, that's the only one. Put it all together now. Draw your graph. Whoops. Cooperate. Let's do it down here. Draw your graph. Okay, so the what do we find out? So the graph is going to cross at the origin, right? It's going to also have y equals 0 as its horizontal asymptote. That's the x-axis. It's okay to cross the horizontal asymptote. The graph is going to be increasing. Let's try something different here. The graph is going to be increasing until you get to 1, and then decreasing after 1. The relative max is at 1, 0.37. So locate the point 1, 0.37. Let's put it right about here. That's going to be our max, right? And then the graph needs to be going up before that and going down after, but we're going to hold off on that. The next thing we figured out was the inflection point. Let's use blue. Okay, the inflection point. So the inflection point is at 2, 0.27. The graph needs to be concave down before 2 and concave up after 2. So here's 2. Here's 1, here's 2. And so I'm going to be going down after 1. And when I get to 2, I need to inflect. And so there's my inflection point, right? That's my inflection point. You can see it should change from concave down before that point to concave up after that point. And that takes care of number 2.